Here is a grid. Starting from the top left corner, walking only along the grid lines in the right and down directions, how many ways can we reach the bottom right corner? Pause the video if you want to give this a try. The correct answer is 126. Did you get it? As I mentioned in the title, this problem changed my life. I remember when my teacher explained this problem to me in the 7th grade, and what I discovered and learned from the solution is one of the reasons why I love math so much today. I wanted to share that moment with all of you. Let's first discuss how this problem is solved. The naive way to solve any counting problem is to make a list of all of the things we want to count and then just count the list. Clearly, this isn't very practical. With 126 different paths, it would take forever to list them all. But more importantly, because there are so many different paths to list, it can be very difficult to manage. I have the full list here supposedly, but there are important unanswered questions. How can we tell that this answer is correct? How do we make sure that we haven't overcounted by counting a path more than once? And how do we make sure that we haven't undercounted, that there are paths that we missed in our list? Let's find another way to represent the path. Here is an example of a path I could take. How would you describe this path to someone? One way is to describe the direction of each step you take. For instance, here, the first step takes us over to the right. So let's write an R to indicate that. The next step goes downwards, so let's write a D to indicate that. Continuing in this way, we make a sequence of letters that describe each step of the path. Notice that using this method, there's only one way to describe the path, and each sequence of letters can only produce one possible path. All we have to do now is take every single path and pair it with its step sequence. This example obviously isn't the same size as our original problem, but the concept is the same. The reason we are doing this is because both of these lists have the same number of things, so we can count either of these lists to get our final answer. But the left list is much harder to count. The right list is much easier to count. Let's take a look at how we would count the right list. First of all, our path must contain 5 steps to the right and 4 steps downwards. This means that our step sequence must contain 5 R's and 4 D's for a total of 9 letters. Had the 9 letters all been different, the number of ways to order them is simply 9 factorial. 9 times 8 times 7 times 6, etc. all the way to 1. This is because there are 9 ways to choose the first letter, then 8 ways to choose the second letter, since we can't reuse the first letter we chose, 7 ways to choose the third letter, and so on. But there are 4 D's. If we fix the other 5 letters, there are 4 factorial ways of ordering the D's. Notice that we have counted all of these orderings, but they all should count as only one of the orderings we want, since the D's are identical. All of the orderings can be grouped in the same way, which means that in order to account for the D's all being the same, we need to divide 9 factorial by 4 factorial. Likewise, we can account for all of the other letters being R's in the same way, by dividing our account by 5 factorial. This expression gives us our answer. However, this is just the beginning. There is an established and simpler way to express this value. Another way to think about how we could make one of our step sequences is to simply choose any combination of 5 out of our 9 positions to make R's. The rest will automatically be D's. We call this value 9 choose 5, the number of combinations of 5 objects out of 9. written like this. So what did we learn? Well, for starters, notice that we started with a grid walking problem, figured out an alternate way to list the paths, then figured out how to count combinations. Thus, the combination numbers are the solutions to our problem. In general, for a grid that has x width and y height, our solution is x plus y choose x. This was the first spark of magic for me. Not only did this seemingly difficult problem have a very simple solution with an explicit formula, it was also the first time I saw a math problem that utilized a formula involving factorials. What's amazing, though, is that this isn't even the best part. It turns out there's another way to solve this problem. While there isn't an explicit formula using this method, the concept is much simpler. Let's label every point on this grid with a number, specifically the number of ways of reaching that point. We start by labeling the starting point with a 1. Some of you might be asking right now why we aren't labeling it with a 0. After all, if you need to end where you start, then you can't take any steps, so does that even count as a path? Well, think about what it means to say there are 0 ways to reach somewhere. If I say that there are 0 ways to get from point A to point B, I'm basically saying that it is impossible to get from A to B. Clearly, it's not impossible to reach my starting point, since I'm already there. And so, we want to say that there is exactly one way to get there. Next, notice that all of the points directly to the right and down can only be reached in one way. And so, we can label all of these points with a 1. This point here is a 2, since there are clearly 2 ways to get there. However, there is a more general logic. Notice that there are only 2 ways we can approach this point. We either approach from the left side or the top side. Therefore, the number of ways of getting to this point is the number of ways to reach the left point plus the number of ways to reach the top point. All we need to do is add these numbers, and we can find the number of paths to get here. We continue this approach and fill in the numbers, eventually reaching the bottom corner, where we get our answer. Pretty slick, right? Well, don't go yet, because I saved the best for last. There's an amazing and important reason why I showed you both methods. So let's label all of the points like we did before. I'm going to do something kinda subtle to the grid now. And there. I've rotated the grid about 45 degrees. Now, some of you may recognize this, but for those of you who didn't, this is a part of Pascal's triangle. Pascal's triangle is the pattern you get when you start with a 1 at the top, then make each number underneath the sum of the 2 numbers directly above it. Okay, let's reset for a minute. So let's label all of our points like we did before, except this time, instead of writing the counts as numbers, let's use the formula we figured out. Since it's the same problem, the values are the same. What this tells us is that Pascal's triangle is essentially a table of our combination numbers. Take a minute to digest this concept and see the connection. Isn't it incredible how a simple addition rule forms numbers that are defined by factorials? In conclusion, we started with a grid walking problem, then solved it in 2 different ways, by using combination numbers and by using Pascal's triangle. This taught us that Pascal's triangle is basically a table of combination numbers. By connecting these 2 seemingly unrelated concepts, we can learn a lot about counting. Any pattern that you can identify in Pascal's triangle can potentially teach us something about combinations. For instance, Pascal's triangle is symmetrical, which tells us that, for example, 5 choose 2 is equal to 5 choose 3. This is merely the introduction to an entire world of combinatorics, only scratching the surface of a ton of interesting, amazing, or downright peculiar lessons to be learned. If you want to learn more, please hit like, subscribe to my channel, and share this video. I will be posting more videos on combinatorics, as well as other math topics in the near future. See you then.